All right, so good morning. Right. So as you can see, people are becoming better and better developers or coders, whatever you want to call it. But there are still gaps. So what I'll be trying to do between this week and next week is to fill in the blanks of what is left as far as coding is concerned. Not all the code, but a lot of it. Right. So today we'll look at examples from the text. Some people have asked me about the code. Some of them we've been skipping because we just pick one and make sure people can code one thing well. But when people get comfortable, I can see people are getting comfortable with sockets, we'll go back and then add in other languages. The main languages in this class that we're using mostly are C++, C, and Java. If you can do the C code, usually you can switch it into C++. Java, most people are already using that. Right. So we'll look at some of the code that's in the text. We'll start with memory sharing memory. Right. So previously we said that if you have multiple tasks, or in this case, right, communication does provide some benefits. Right. So we are going to look at some of the other means. So we saw sockets, or we've seen sockets, but I'll do an example that includes memory sharing and discuss how the code is working for those who might encounter this in the future or want to use it in any project this semester. There are more coding projects coming. Right. So let me fire up my virtual box. So we'll look first at some examples. So I'll pick each one, discuss the code, take questions, and run, so we'll see. So we'll start with memory. Sorry. Memory. Speed thread. Okay. I think it was a long time since I wrote this, so I'm trying to remember where things are. Okay. Start. Oh, come on. All right, so this is it's code from the text, and what it has is, it's showing you how to share memory, right? So the code looks very much like using a file, right? So these are just important principles we want to get used to. I know people can do variables, they can do files, but we just need to pick up a few new techniques in this class so you can solve other problems. So what you'd see is, I've changed the code from in this one a bit, in that in the text sometimes, I don't know why, they would write something like in size and forget the equal sign or something. So when you copy the code exactly, it may not compile. So if you're copying code from the textbook, just pay attention to the command, the errors that will come when you compile. Right. So the first one is to define the size of the shared memory. So here you define the size of the shared memory. There is also a var name that represents the file name that it will use. So shared memory in Linux is behaving a little bit like a file. So that means that there is this block of area that will be in its memory that will be called by a file name, so that others can open and write to it. Now, what this one was doing was it created, and this is to illustrate how you can put data into shared memory, right? So you can create your normal, so this is just a pointer to a string, hello, a pointer to a string, world, right? And what the system caller uses shm open. So it gives the name of the file. It says, I want to open and create. So if it doesn't exist, you create it. The permissions 666, what would that mean? Okay, so read, write, but no execute. Right. So remember, the bits, if it's 777, means you can read, write, and execute. If it's 666, it means you can read and write, but you can't execute. For the user, the group, and everyone else. Right. So you also have here, it says F truncate, meaning that it can resize so that it knows exactly how much it's using. So this first one will create the shared memory. So the shared memory is now like a file, right? So it's creating the shared memory. And what it's doing is it puts a pointer, so it maps the data in the shared memory to a pointer. So it starts from some location to the full size, right? And how it is putting data into the shared memory is it's doing sprintf. And I think you have seen sprint already. Sprint or printf. You've done printf. Printf prints to some, you can print to screen with printf. Right, but with sprintf, usually you specify the location or the port that you're using, or the stream you want to print to. Right, so sprintf, there's a pointer, meaning that I want to print to that pointer that is pointing to the memory location. And it's printing the size of the message. Right, so that's the first one, printing the size of the message. And then it moves the pointer by some amount. So remember that the message that it created was a string. It was hello. Right. So what it does is anytime it prints to that stream, it will move the pointer forward a little bit. So the size, so if it says hello world, it has to move it, the first character. And then what? That's another print. So the pointer has now what? Has moved along the file. So that's an important point. So the pointer, they don't just do sprint. The normal way you do printf. Printf usually print, you don't worry about it because the information comes to the screen. But when you are dealing with the memory or pointer data, what happens is when they print, you print to a position in memory. That means that when you put some data there, you have to move your pointer forward by the size of whatever you are putting there. So if it's a string you put in there, you move by the size of the string. If it's an integer, you move by the size of an integer. So that means that string length, so that means it's just bytes. So he moves forward by how many bytes he has. And then prints again to the pointer. And then moves it again by another string length, so that the pointer has now moved forward to the end of wherever his data is. So someone had a question.
You did mention that you were printing the size of the...
Not printing the size. After you print, you move the pointer forward. So the pointer is the location where it's currently pointing to. Right? When you normally print to screen, you don't worry about pointers. You don't worry about where the cursor is. Right? But for this one, because you are manipulating memory, and it's treating the memory like the screen, that means that when he says print, he prints from that location. So start from 0, you start printing, putting the data there. So if you don't want to overwrite your original data, you have to what? Move the pointer forward, right, before you do the other print. So I'll do one, this one has moved. I'll run this one where the pointer has moved, and I'll do when I don't move the pointer, so you can compare, right? So this is code for a producer, so or someone who is making some data for someone else to consume. It's a simple hello world, but the point is you can use this in many other ways. So if you have a web server, so today all the ways we're looking at, I talked about, few of them. So the ones I listed, I said you could do memory sharing. We'll look at pipes, we'll look at sockets. So these are all just what different techniques that will allow different processes to share information. So previously, we were told that processes were not allowed to what? Share memory. They were isolated. But if they want to share memory, then they have to make a system call shared memory open to tell the OS that they want to share some memory, and the OS will make this memory available. Right. So let me compile this. So to compile is GCC. Okay, so if this happens, so this is one of the things that I should warn you from the text. you won't always be using just GCC and then the name of the file. Sometimes you can include other, so this one, for example, I just remember a few of them. Real time. So there are some libraries that GCC, if it doesn't include by default, there are parameters that you can include. So please, if you compile something like this and it says undefined reference to some system call, you can just Google it or search online and it will tell you what parameter you must pass to GCC so that it includes the appropriate libraries. Right. So some people are trying to run the code in a text and they're running into issues. So if you run into an issue and it says that, so you have included everything and it says undefined reference, especially undefined reference, it just means that the compiler doesn't know that it should include certain libraries. Right. So you realize that like Java, there's something like import. So at the top of your file, it does include, I think I included some of these twice. Okay. No, I didn't. That's good. Okay. That's very good. So it has included libraries. But when it's compiling, it needs to tell the system which libraries are included. The common libraries will just compile. But if it's a library which is not very common, some of them don't just compile by default. You need to, so in this case, I'm specifying using LRT. Right. So what I'll do is I'll say output to a program called P. So my server is living in a program called P. Right. The interesting thing about this is when you run P, when you run P, it has finished. It's finished running. But the memory, the shared memory it has created is still there. It is like a file. I hope people understand the point. Shared memory, a lot of things in Linux are like files. So the file is one, but shared memory itself behaves like a file, meaning that right now, even though this program has finished running, so it didn't really do anything. I just, within the program, within the program, all it did was to write some data to shared memory. But even though the program has ended, that shared memory currently, so long as the machine is on and it doesn't go off, in memory, that data is still there. So what we are going to do is we are going to look at the client code that can access the memory. So the client also starts almost the same way. But what he does is he says, make me a size, same thing. Make me a file name. So it means that the OS, the operating system, is now, because they are all using the word OS, remember the first one also called this OS. Right? So it means that in memory, there is, so this file is not what? It's not on the disk. It's in memory, and it's being shared. So it means if someone else says, okay, I want to make a file called OS, and this file is a shared memory type, he is read, okay, I just made it read write. You can make it read only. The book used read only. But I made it read write to show you that you can have what? Multiple processes which are running and operating on, it's like a file. Right? The nice thing about this is it's not like the normal file where one person opens, the other person can't write. Right? So this is now like memory. So it means that anything that someone writes to, the other person can pick up and use. Right? So he does the same thing, but what he will do is he also does an M map. So he maps it to a pointer. And he then prints. But when he's printing, he's saying, I want to print based on the start of that shared memory. I hope people are understanding. Memory is just data. It's like a character array, right? It means it will print until it sees, I think, \n or \o. A string is usually terminated by some terminating character. So by doing this, by doing printf, so it's printing. But note that it's printing what? The shared memory location, the pointer. He also made one. But he didn't what? He didn't sprint f to it. He didn't print some data to it. He is instead saying what? Print that pointer. This is different in the way that C and Java behave. In C++, almost any pointer, you can try and print it. And when you say print, and this was last time I said to you that I hope people are paying attention to the fact that there are these %s, %d, %i. So as far as C++ go, if you're telling him to print, and you say %s, that means he's going to look for a string. So he's going to go through that data location. So the interesting thing is, you can print almost anything you want. Any pointer address that you want. So I could do pointer plus 1 million and try and print. Of course, some of you will give me an error if it's out of my range. In Java, you are often limited to what? The data type. When you are printing, it forces you, okay, this is a string. It doesn't tell you, oh, I can turn a string into this. It just says, you are printing. The data is there. But in C, C++, you have access to the pointers. That's data pointers themselves. And you can treat it the way you want. So I could have tried to print this as an integer, as a string, as a decimal. Just depends on the %s, right? Or %d if it's decimal, right? Now, in the book, they removed this shared link. So there is a system called here, which is called, so that means there are two of them, SHM open, which will create a shared memory, and SHM unlink, which will what? Destroy the shared memory. So I will not let him destroy it. In the textbook, they destroy it. But I'm going to keep it there so that you realize that what? You can keep running. That means that it's possible for programs to share some common information amongst themselves, right? That means that all they have to do is someone creates a shared memory, and the others can what? Go to the shared memory and get various information. So let me compile this client. I'm going to compile him to C, right? And then run C. Oh, sorry. So you see he's printing hello world with the asterisks. And I can run him again. He's printing hello world. So, but if you look into my directory, there's nothing called, okay, let me do SH so people can see. There is nothing called capital OS, right? There is an OS folder here, but my OS folder has a code in there. But so the interesting thing is, I hope people are realizing that shared memory, that means that the data is not what? It's not on the disk. Right? That's my point to you, that for shared memory, it's like a file, all right, but the data is not on the hard disk. It's not something I can do ls and go and print it. It means it's only accessible by opening this virtual file, which is pointing to memory, and getting data from that virtual file. So that is how shared memory works. So people understand the point of shared memory. Right? And shared memory, if it's shared memory, it means what? It's not going to rely on hard disk. I expect it to be faster than hard disk. So it means that certain classes of programs that need some speed could rely on this approach, where they make these pseudo files. So these files are actually in memory. So you can think of them like in-memory files. And they can use and access them. They don't go all the way to hard disk. The only problem is, if you shut down the machine, if I reboot this, the data will be what? It will be gone, because it's a memory data structure. Question. Say it again. So it depends on how it's actually implemented. So you realize that a lot of these techniques that we are showing you, that means that there are so many ways you can implement all of these things. I hope you understand. So I'm giving you all the things. Like right now, people have seen sockets. It's possible. So if someone wants to say, okay, I want to make an operating system, I want to share data. So I've given you the list. You can do either the sockets. That means that maybe someone has Control C. The OS can take the data, send it to some server somewhere, and then can pull it back out. You just need to use one of these. But shared memory is definitely one way to do this. Right? But that means that the person who wrote the OS would say, whenever I see Control C, I'll copy something into shared memory. But right now, the clipboards have become more advanced. They can hold multiple things. They can expand. So I think, aside this, even if you did this, you must make sure that you expand the memory space over time, because I think for most OSs, it won't complain. It will just, I think Microsoft will sometimes warn you. The data you're trying to copy to the clipboard is very large. But it does copy it. So it's possible to do something like this. Right. Now, logging files. You can log, but remember that shared memory, it doesn't hit the hard disk, right? So it means that if it goes off, the information is gone. Oh, okay, you mean locks, not log. Okay, so for locks, this is a way to share information, but there are some libraries which you can use locks with. It's a good idea if you're going to have multiple people reading to have locks as well. So there are locks in C, C++ that you can use. But I'm just illustrating for memory sharing. Right? So he's right. If you want to have two people, so right now it's just one producer, one consumer, that would work out. But if you want to have two people communicate at the same time, right into it, then there has to be some protocol, some agreement. So there are many that in the past I've done, such as, okay, everybody will have some space. So let's say you have a space which will be your inbox, and a space for your outbox. And I'll have a space for my inbox, a space for my outbox. And that means that whenever I am sending information to you, I'll write to that space that belongs to your inbox. And if you're writing to me, you write the space belonging. So you can have some protocol. Now, in this example in the text, all they are doing is they just use, Emacs. Less p.c. they just use one thing called OS. But you don't have to limit yourself to just OS. You can make multiple shared memory locations. I hope you understand. So that you can say, okay, this is data going to this program, this data going to another program. Right? But you just have to come up with some protocols, some agreement as to how information is moved in and moved out. Okay, so I promised that I would make it so that we would not move the pointer. So I want you to see what will happen if we don't move the pointer. So not moving the pointer is, I would print the message 1, which is a hello, into the shared memory, and then I will not move the pointer. Right? So this is pointer plus. I'm not going to move the pointer. I'm just going to print again to the same location, the world, so that we'll see what was going to happen. So compile, GCC P. Okay, so he's written and C. But what does C see now? He just sees what? World. And that's because the parent, when he printed the first string, he didn't move the pointer forward. I hope people are understanding. So it means that when you're dealing with shared memory, with this approach, what you do is you can print your integers and such into the memory location. But just make sure that after you print, you what? You move the pointer so that next time you are printing, it starts from the new location. So this is now just printing world, not hello. Because what? I overwrote it by the way I printed. I didn't shift the pointer. I just printed again. Right? So this is the conclusion of shared memory. So those who are asking and wondering how shared memory works. Right. So any questions about shared memory before we move to the next one, which will be pipes? So today we are looking at all the codes that we've skipped. So any questions about shared memory? Okay, so there are different protocols, right? If you look at sockets, sockets had to go over the network, or you could go over the network. You know, you could specify some local host or some host name plus a port. But with shared memory, he's not going over the network. He's what? Right on the machine, two processes that want to communicate. But they need to have some shared space to communicate with. And shared memory can accomplish that. Right? You can use sockets as well. But the nice thing about this is you realize even when the programs go off, the data doesn't disappear. Right now, P is not running, C is not running. But what? The data is there. Anytime C runs again, he can... Right? So even though the programs have stopped running, the shared memory that was created still exists. Until someone... So how did I say you remove it? So in order to delete the shared memory, you'd have to... Sorry. There is a link. Oh. You need the system call unlink, so that what you can delete that part of memory from, that named memory from the block, so that the OS will remove the sharing, and someone else can use it. But right now, even if the program isn't running, because I've created it, it's almost like a file. But as I said, it's like what? A file in memory, and you can use it. But the only thing is, even if you die, the data is still there. Compared to sockets, if the program dies, the information gets discarded. Right? And in sockets, you realize that when you are sending, someone has to what? Someone has to receive. If you are receiving, someone has to send. You will block. But this one, you are not going to block. You're going to say, oh, here's some memory, I'm getting some data from it. Right. Now, okay, so what I said was, anytime, sorry, I have to stop. Okay, it's stopped now. P.C. Right. Now, the way that this works, so you can look at the function. This function is called, it's not printf. I'm using sprintf, right? And what sprintf, the function will do is, it would allow you to specify what location you are writing to. So if you provided something like system out or system that means that would be my first parameter. So it's saying, now, it's not going to assume that I'm printing to console. It's assuming I'm printing to a file or to some memory location. Right? But when I print, I should make sure that I move the pointer. Because if I print hello and I don't move the pointer, if I print world, it will overwrite what I've written hello before. So that's what happened here, in that the first time I printed, I was moving the pointer, which was by doing, and what I said was you can always get, sorry, I use string length just to see the size of it so that I can move the pointer by how large that string is. So I can move it and then I can print after. Right. So for example, if I print and I do, okay, I'm going to move this forward by a bit, +5. So there'll be some junk in there. Right. So that means that now, instead of just moving it by the size of hello, I'm going to move it forward by even a little bit more. Right. Oh yeah, PTR, thank you. All right. I am going to unlink, sorry. Okay. The reason why I'm unlinking is I'm going to make sure that I get a fresh block of memory. So I'm just going to run the code for the client. That will unlink it. I hope people understand what I mean by unlink. When unlink is called, it will delete the shared memory. Right. So if you look at this, it says shared memory. SH open, this one is saying open for read write. Right? And the name there is the name OS. So it can be some name that you are using. You can say OS. It's just like, what will happen is the OS will keep track of that name for you. So that anytime you are using it, that user, you can access that shared memory. So within your space, all the programs that are running there, if you created something, so this guy, for example, sorry, or even I could call it something else. Let me call it OS2. So that means that what? I'm creating what? A shared memory that I'm calling OS number 2. Right. Let me compile the client. Right. And let me also get the server, who was this guy. I'm also going to have him work with what? OS number 2. So it means the file names must correspond for all the people that I want to share the shared memory space with. All right. And what I'm doing is, I'm going to print the same, it can even be a different, okay. So I can say string 1, so I can print the first string and another string. Right. So at least I have 2 strings going. So after I send the first string, I'm going to move the pointer forward, not just by the size of the first string. I'm just going to part 5 so that I jump before I print more information. Right. So compile this one as well. P and output to P. Okay. Okay, so he's run. So you can see that it's printing some junk. Is that string 1 and then it's just stopped. Right. So it means that if I'm not letting it follow exactly, so sometimes, for example, if I don't put anything there at all, you can sometimes get junk, but this, it's terminated a string. I'm going to do one, I'm going to do OS3, where I'll just what? I'll move it forward without printing the first one, just so we can see what's happening in memory. So, trying to make it force an error with this, I'll make it make an error, for sure. Okay. So what I'm going to do is, I'm going to call this OS3. I'm making a lot of shared memory spaces. So, okay. So I've made a new one, another one, now called OS3, same size. But what I'll do is, instead of printing, this is wrong type of, okay. Instead of printing, I'm just going to what? Move the pointer forward. And then what? Print some data starting at some offset. Just so you can see the behavior. So, GCC, okay, it's compiled. And that means that what? I have to modify this one as well to read from what? OS3, that shared memory. So it means that if I'm making some application, I have to plan what shared memory locations am I reading and writing from. Right. I will not unlink this. Okay, and let's run the P first. Oh, the C didn't even get anything. That means there's almost no data there. So if he tries to print and he doesn't get, if he meets either a null, so remember null is like empty. If he meets a null or \n, I'll not get anything. But as far as printing, you can often print, sorry, let me do this. It's evil, but I'll do it. Okay. Okay. So I'm just moving the pointer off by 10. Just moving the pointer. Okay, compile again. Oh, he's still not getting any good. It's all blank. Maybe the memory he's getting is now. But this is just sometimes. So what I was doing here, sometimes if you haven't put anything in memory, when you try and print, you will get junk. But in this case, he's not printing junk. Maybe he's just initializing it to 0. Let's play a crazy trick. Let's make him do 4. He's going to open it for read-write. He has not created a file yet. This should be an error because the file doesn't segment it. Okay, because the file what? Doesn't exist. He just opened it with what? Read-write. So you can treat it like a file, but the only thing is make sure you put data there before you get data out. Else it's just what? It's just a block of memory. Your question? So I'm compiling GCC LRT with real-time CC, output it to the program binary C. So I compile one to C, and I compile the other one to P. I believe I'm doing, where's P? Output to P. I just showed you that you can crash if the memory hasn't been initialized. That was my last one. Right. So if the memory space doesn't exist and you try to read it, you get a seg fault. And seg fault because the memory doesn't even, you're just trying to read, but nobody has created it. So you're going to crash. It doesn't belong to you. Right. So with this, we are ending the memory discussion.
I think what I was asking was, when you change the OS to, you change the software OS 1 to you ain't compile it, you just compile it.
Oh, I've been compiling both of them. Are you sure? Okay, this is still going to crash. Let me see what is in P right now. Emacs P.C. Okay, he is OS 3. And C is... Okay, he has gone to OS 4. So if I want him to work, I have to put him back to OS 3. Right? Okay. No, he's not. Okay, and that's because C is not reading from a good location. C did an offset, so he wasn't getting anything. So if I did this, then he should be fine. So GCC. Oh. That's very strange. Oh, P didn't write to the beginning of the file, right? I made P start from an offset. Here, I didn't let P write from the beginning. Okay, P and then C. Okay, so now you can get it. So you can have this approach to share information as well. All right. So from this, we'll move to the next one, which is pipes. Right. So we are going to look at 2 types of pipes. The book has unnamed pipes, but today I'll also discuss named pipes. Right. So what a pipe is. So there are many, many ways that programs communicate. So this is a nice, popular, what's it? Maybe an OS type interview question. What are the different ways a program can communicate? You can use file as a simple one. Everyone can do file. If someone writes it, someone reads from it. The second one is pipes. Right? So piping is something that the OS can do to send information from one program to the other. Usually without what? Writing to a file. Right? So memory is the other one. So yes, you can do files. But memory is like a type of file, but memory belongs to you. But you can do shared memory, in which case you can what? Share something with someone else, even though it's not in your memory space. You write the shared memory. Now, piping is another one. Mostly what people do is they can do things like ls, and as you can see, you can do word count. So that means ls by itself is sending information to a program called what? I think this was one of the, it was in one of the questions. You have to use WC, word count. So word count is a program, ls is a program, right? And then that means, for example, if I wanted to count the size of something, like what's the size of this? The words in there. Less by itself, less p.c would output all of this. But then I can say less p.c and then send the information to another program. When we were in school, we used to do this a lot when we were testing applications. I have not seen people actually really push the boundary as far as this. But if you have a console application, you don't have to keep typing things. You can have one program that writes output to screen. Another program can be reading the output. So if I wanted to test some application by typing some commands into it, what we'll do is we'll have one program that generates printing to screen, another program that does reading from screen. And by doing this, I can pipe from one program to another program. So the OS provides this mechanism to allow processes to communicate. So you don't have to write extra code to use this approach. Windows does this, Linux can do this. Right. Now, what some people can also do is you can also pipe to a file, in which case you don't use the bar, you use arrow. So I can say less, and I can say less PC. So the information, I think you also saw this, was in one of the exercises, the practice, sending something to a file. After piping, so this is the normal pipe. Sorry. The normal pipe uses the bar, right? But if you use an arrow, you can send information to a file. So as a program is running, you can pipe information to a file. So yes, when we're testing programs, what we'll do is sometimes we'll start the program, nobody is sitting at the computer, you just do arrow, you pipe, you go away, 2 hours later you come back, your data is in a file. You can see what the output of the program is. So there are many benefits of pipes. Now another one is sometimes you want to be able to tell one program to go and use a specific, like you want two programs to communicate, but you don't want it to be, you can't really type. It's like if a server is running, like Apache is running, and he wants to send something to his children, like he has made several children. It would be nice if he can send information. So memory sharing is one, but piping is another option. So pipe, that means you behave almost like a real file. You don't have to do this pointer offset thing. It will just be like a file. You read and you can write to it. So let's look at the pipe example. Code. Okay, I have my pipes. Okay, so the pipe has some forking in it. So what you'd see is when you are creating a file, you say fopen, right? You say fopen, and it gives you a file descriptor. A file descriptor meaning some number that when you are printing, so you can do sprintf. So that you saw the printing I did when I was printing to memory. When you open a file, you can do the same printing. If you have a file descriptor, it will work. So what we are doing here is now, a pipe now behaves like, as I would say, two-way pipe, like the way you used to play when you were children. Someone holds a string with a cup. The other person holds a string with a cup. So a normal file that's simple. I'm going quickly because I'm running out of time. I have 30 minutes. Okay, so I'll slow down a bit. Okay, so a normal file, if you open a file normally, you can usually just read to it or write to it. But what a pipe will allow you to do is you can read and write at the same time. So it's a little bit like a socket, except that it's not over the network. Two programs can securely, so without any snooping whatsoever, the OS is going to handle sending information from one program to the other. The way we are doing this is we are first defining an array. So now it's not just one variable, int, representing the file. Then when you do fopen, you get what? A file descriptor. In Java or C, you always get some file pointer that you can use. But this one, pipe uses two integers, an array of two, meaning that one end will be for reading and one end will be what? For writing to the same file. So this is, for me, when I heard this, I was very excited. I was like, wow. So now I have a program that's running. One is sending the information, and one is pulling the information. It's a little bit like a socket, right? But the difference is that now it's a file. Right? Some people also call this anonymous pipes, meaning that when this pipe is there, no other process can figure it out. Right? Because the file doesn't exist. So remember, if you have a real file, it exists. If you say shared memory, it has a name, so other programs that are running in your space can see the shared memory. But with this pipe approach, this specific one, there's no name to it, right? It just says pipe. And that means that the program that is running knows about it. But other programs have no idea. It's not something that you can figure out, someone made a file somewhere, I can go and pick it up. It means that two programs can communicate using this piping approach. So what it does is it says, create a pipe for me. And there are two. One is the parent, one is the child. There's an integer. So what they are doing is, there are two numbers. The reading part is 0, and the writing part is 1. They are just using the numbers, just so they can, because you've made an array. Two integers, which is this one. So 2 integers, right? So they just use 0 to refer to the first slot, 1 to refer to the second slot. But by convention, they'll just say one person should close. So in this case, PID greater than what? 0. Oh, sorry, this thing is moving. I have to speak. PID greater than 0 is the parent. So the parent is going to say, close the read end. The parent is saying he's not going to read. He's going to what? Write. So that means that the parent is planning to send information to the child. And the child, meanwhile, is saying, I am not going to write. I am going to what? To read. That means that now you can have communication between the parent and child. If you are a process and you create a pipe and you read and write to it, then you are doing your own work. But it's much more useful if there are two processes, so that you can create this pipe. So one process will be listening, one person will be what? Writing, and then they can communicate. Right. And you can see this printing again. There's a message, so the message is simply greetings or hello world. You can do anything you want with this. Right. It's not really anything complicated. Right. And then one of them would be for the parent, and one of them would be for the child. But when the child gets the information, he prints it and says, I have read whatever you provided for me. So it means that what? Two processes can run. I'm going to add a sleep in here, just for fun. Okay. Sleep for 10 seconds. I think I should have included pthread in this, but anyway, let's do it. It's a system call. It should work without any threading. So gcc pipes.c output to p. Too long. Okay. Let me see how large my integer is. Okay, yeah, that's way too. Make it 100. Okay. Just a sec. I'm wondering if I've slept for too long. Please hold. Okay, so the parents, okay, you don't sleep. You close. Okay. Without the sleep, the information will come immediately. Just a sec. P. Right. So this greetings, how are you, is being printed from what? The child. The child, there's a branch there, but that branch is only being executed. Where's my Emacs? Sorry. The printf is only happening within the child section. Right. But meanwhile, the variable itself was, for example, here. You can, so if you are designing, you don't have to always define a variable somewhere here. You could have it, sorry. You could write another message. Let me just do this. I'm just showing you that you don't always have to use what's there. You can extend the idea a little bit. So I'm going to make a new message, message 2. And I can send that one instead. Where's my write? Okay, file description, write. Message 2 plus 1. Hello, and how are you? So I'd say new message by parent. Right. So what I'm showing you is currently both of them have, so someone can argue with me and say, oh, but the child also has the same memory. That's why he's printing it. But I'm just doing this to prove to you the parent here is creating a new variable. The child won't get to this code. It's the parent who creates this variable, this data. And when the parent creates it, he's going to use the write, so he says write, to send the information to the child. So let's run this, compile and run this. GCC. Right, read new message by parent. So it means that you can also use this approach to send information from one program to another. So one program can start, he can make a child, and then what? Periodically, he can send him some information, and the child can perform some action. So pipe, this type of pipe is also possible. This one is called an anonymous pipe. This is the one from the textbook. Right. So it's like a file. So I hope people are realizing how this one is behaving. Emacs. Okay. So it's a lot like a file. You can close, read, write, except that what? There are two parts to it. When you create it, when you call the system call pipe, you get two numbers in your array, so that you can use one for reading, one for writing. Right. I hope people are getting used to these new concepts. So we are extending everything you have been doing. You are used to files, but I'm now telling you there's something called pipe. And when you create it, it's like what? A file with what? Two-way communication. Right. So you could have something like a database system. This can be very useful. From one to the other, you can send information. It's like one is writing and one is what? Pulling from it. Okay, so that is another one. So any questions about pipes before we move to the next? Well, we move to the name. This is anonymous pipes, right? No name was involved. We'll look at one with names. Your question and then hers. That was just because the parent was ending. If he ran in an infinite loop, so maybe I think in terms of maybe a server with a child, if he was running in an infinite loop, then that just means that he will just do a while loop and will not close it immediately. He can keep writing data to it. So this wasn't altogether necessary. I think it was just by convention that if you are using this, what happens is you should make sure that you don't cause any, what's the word? You don't create any confusion. So what happens is, by convention, you agree that one person will be writing, one person will be reading. That means if I want to do two-way communication, I can do what? Two pipes. That means you will close one end of one pipe and use it for reading. I'll close one end of one pipe and use it for reading. So that means two pipes can be used to do two-way. So it wasn't necessary to close. I'll compile and run it. Right, it will still work. It was just by convention. They were just being good coders to say, let's all be well behaved, right? If you are not going to write, close the right end. If you are not going to read, close the read end. It's just good coding practice. And when you finish, I know some people don't close but it's not very clean code if you don't close it, because it will be hanging, remember. I hope you understand the point. At the point of the fork being created, the parent and child both have the same file descriptor. That means that they both have the same files in their memory. But what happens is, if you are not using it, it's good to close it so that the OS can remove it from your resource list. So that's why the moment they are not using it, you close it. You are using less resources. Then you use just what you need. I hope you understand the point. Okay, so your question. Okay, so this one, for example. So I keep using web servers as an example. Right. So there is an assignment coming up very soon. And you'll be allowed to use. You need to do more code. I want you guys to be very good. Very, very good. Right. So the assignment coming up has to do with making a web server. And when the web server is running, it has to make children. And the children will have, like maybe a request comes in, someone types www.google.com. It comes in. You have to give a response. Right. So what you can do is, one parent can make multiple children. Right. So maybe 4 children. And as the information comes, the parent can write different pipes. He can make 4 pipes and say, write the first pipe. And that means that the information picked up by the child will read it, perform some action for me on my behalf. Previously, what we were doing, you saw the exec LP, that coding exercise, where the child is called and the child runs a specific path. He just goes and he's told, do ls, do who am I. But with piping, what you can do is, the child can go and wait to get a specific instruction sent by the parent. And now the parent's instruction can be what? Ad hoc. Because instead of me typing it in or having hard-coded, it could come from the web. Like it means the parent can get some information from a socket from online, process it, send a command to the child. Right now, the assignment you are doing, you are sending a command over the network. But with this one, they can all be on the same machine. No network involved. The parent can send information to the child. The child can then perform a specific action for the parent. I hope you understand. So it's all about communication. All of these are just different ways to communicate. And it's possible to accomplish the same thing with shared memory, with sockets, with pipes. except that depending on which you pick, there will be some nuances. So for example, this one, you realize I don't have to worry about the shared memory one, where you have to move the pointer and all of that. This one is, I think, very clean. You just open it like a normal file, you write to it, the other person picks it up. But of course, once the program dies, the information is gone. Shared memory, even when the program was died, the shared memory still existed. So there are advantages and disadvantages. I'm just showing you all the different techniques, so that if you encounter a problem, you can pick one of these tools to fix it. All right. Now, the last one, or last but one I should say. I have so many code to share with you guys. So many. Hello. Normally, I just code what is in the textbook. The ones that are not there, I'll put up the links. But I just picked the code from the text. But I think I made a good point. I'll make PDFs out of these. I don't want you to just be copy-pasting code. I want them to try it out. So I'll make PDFs out of all the codes I have in this folder, so people can look at what's going on. Right? But a lot of them come from different sources. So either the text, or if there's a specific link, like this one. This one is from another textbook, Linux Programmer's Guide. I think it's also online. So what this one is doing is, we talked about what? The anonymous pipe. The pipe we created didn't have a name. But now you can have what we call named pipes, meaning that the pipe can work and have a specific name. So in this case, this FIFO file, and pipes, you also hear the word FIFO, like first in, first out. So it's almost like the concept of it's like a queue. Data goes in on one side and comes out the other, first in, first out. So if you hear FIFO in Linux, someone says it's a FIFO file, it usually means what? A named pipe. A pipe that has a name. Right. So now this one, you realize that it looks very similar to the other one, but the one where it says CHM open, where you're doing shared memory. So this also says open, making a node. There is the name, the type, and then again 666. Sorry, 666 seems to be a common example. Nothing going on. I just copy pasted. Okay, so this one will make a file, and then can open it. So you realize it's almost the same principle as the other one. You do a chmod, or that one was a CHM, CHM open, and then you get a pointer. You can open the specific. So the first one here makes a node. MK node makes a file node. So a file node is just like a pointer to a file, a reference to a file. And then I can open that specific file. So now at this point it looks like a normal file. Right? And then it says, get me some information into the pointer, and then he's going to print some information and then sleep. So this one is just going to work like a parent-child. He's doing receiving. Okay, let's compile it. This is one part. Let's look at the other part. The person who is going to be sending information. No, there should be another one. So many codes, but we'll do it. Good, found it. Okay. So this is another one, and what he's going to do is he's going to say, I'm going to be. So this one, I think this example is very good, showing you that you can use arguments. So what he's doing is, I'm going to pass some arguments to the program. And that argument that I pass will be sent. Okay, where's my argv? Okay. Here's my argv. Those are my arguments, right? That's my argument count. So it's just like Java. In Java, you do what? Public static void main int, and something like some args in there. This is the C version. So there's an argument count and an argument array. So all this will do is, he will also fopen that file. Except that now that file has been created as a first in, first out, meaning that it's going to be a type of file, not a file where you open and no one else can open. This one too can function two-way. You open, it can still be open, and another one can also open. But the difference between this is that the two programs are not necessarily parent and child. In the previous one, remember it was anonymous, meaning that the integers were created within the program. So if you didn't make a child, the child didn't even know the ID of the file that's created, the pipe. But in this one, it's a name pipe, meaning that it has a name. So similarly, the name is here. It's called my FIFO. Right? And that name, once it opens, so he doesn't have to do anything complex. He treats it like a normal file. He says, open the file. The OS will open the file for him. And then all he does is he puts his data into that file, and then he closes it. And he's like, wow, I finished. So that means that now you can have two programs that are what? Running. One person is putting in data, and one person is what? Receiving the data. Right? So the same concept. So let's do some compilation. So GCC for the client output to C. Okay, he output. And the other is the server. And the server is going to output to S. Okay, so I'm going to run the server first. I've run this before. The file, I create a pipe. And it's still there. So it's still, this one I did from yesterday. It's still saying, hello, how are you? Right. What I'm going to do is I'm going to switch. There's a counter going, so that when I switch back, you can know that it's moving. So there's one program running who has received some information. He's just what? Repeating the information over and over. Let me start a new terminal. Right. Was it in shared disk? Code process. Okay, so now I'm going to run the client. Right. Now the client says that I should specify for him some message, such as this is an interesting example. In quotes, because it was supposed to be an argument. So I put in quotes so that the whole thing gets sent. Now I switch back to the first screen, and you see that this guy has received the information. This is an interesting example. So now you can have two programs using pipes, but the only thing is that now now, there are two programs that are what? Sharing the information. It's no more a parent-child connection. It can just be what? So long as you're in the same OS, one person is writing to it, the other person is what? Reading from it. And nobody, this guy hasn't closed it yet. He's still what? As you said, last time you asked me, why did he close? The other guy wasn't what? He wasn't continuing reading. But in this case, the same thing is open in two places. And what? We are all reading and writing at the same time. So pipes have that behavior. Right. One person is what? Sending information in, the other person is pulling information out. And this can also work with the client server, except that this doesn't use a network. This can be on the same machine. Right. So today we are seeing a lot of exciting things from the textbook, right? So we are seeing shared memory, which was this SM open and SHM and link. We're seeing this thing, which is the pipe. And you pass in some array that has two things. We've seen this one, which has a make note. The make note function can do much more than just FIFO. For those who are very interested in finding out all that your piping can do, if you do man, make note. Okay. So there is, let me see. The make note can create a block, it can create a character file, it can also create a FIFO file. The FIFO is what I'm calling, or it's generally called, named pipes. It means that it's a pipe, but what? It has a name, the OS will keep track of it, and two different applications can be what? Can be writing to the pipe at the same time. So it's a bit like sockets, except that it's not identified. Sockets had to have what? An address and a port number to access it. But with pipes, you just need a file name, so the OS manages it. Right. So how people are getting cool with all these ideas? It will take a while. Don't worry, you'll be good. This semester, I want to make sure that people can really do a lot of these things. Because there are some semesters where I'll mention it, but nobody tries it. So what I'm going to do is make sure that there's going to be some programming that would force you to do all of it. Okay, so the last one that we'll look at. So we've seen sockets in C++. So I'll put up, we've seen the Java one. I'll put up the one for, do I have the code running now? Okay. I'll put up the links for this code. There's a very good site that has tutorial. Oh no, this is from the textbook. Okay, this is from the textbook. So let's look at This is just threads. But it's good to look at threads. Okay. So we did threads in Java. This thread version is, let me zoom out a bit. Right. So this version of threads is in C. And what you are doing here is, there's a function here called pthread_create. Right. So, but this one you don't need, in Java you have to do runnable and all of that excitement. For the C version, you don't need to do runnable. All it needs to do is, you need to make sure that you include the pthread library, which is this one. Right. And then you specify the attributes of the thread. So pthread init, initializing with the attributes. The attribute is just a pointer, which is pointer attributes. Right. And then he calls it, but passes a function. So this is a null pointer. So it's a function that can function as what? An entry point. Meaning that when I say pthread_create, it's going to run the function that's pointed to by runner. For the Java one, you have to do something like make a new thread and do a start. For the C version, you don't need to do make a thread, object, and then start. In this one, you just have functions. And all you do is, the functions must have, so you can see they have star in there. Meaning that it's a pointer. Right. So I can pass that to the thread and pass also, so this is an argument that goes into this param. So he can then pick up the parameter that's being passed and then do some calculation for me. Right. This specific version, I think it's from the text. What it does is, the parent will create a number. So people keep asking me, parents and children. Parent creates a number, gets from the argument, passes to the child. The child then does, Come on, move up, move up. My runner. Oh, keep moving this thing too far. Okay, so the child in this case is doing a simple summation. He takes the number the parent provided, does a for loop, and sums up numbers from 1 to that number. So you can have this parent-child relationship. Except that if you are doing C and you want to make it work, just use pthread and make your functions, instead of the other one where you just call the function, you do it, you say pthread, you pass the function name, and then any arguments you need to pass to it. So this is also very nice and very lean. I tend to like this as opposed to the Java one, but everyone has their preference. Right. So if you are doing a project and you want to have, instead of processes, you realize that processes, what? They are isolated. When you do a fork, everybody has his own memory. But with this one, right, what happens is, if the parent comes back and prints the sum, because they all share the same memory, that variable that is stored by the child will be the same one that what? The parent will print. Because now they are running in the same memory space. I hope people understand the point. Just the same way that Java was running. In Java, we did something like a linked list. And when you put it in, the other people could access it. So in this one, that means if I want to have multiple people working in the same memory space, in C, I will be using pthreads. So this code is exactly, well, it's from the textbook. My only warning is, when you are compiling this, I think I should put, so for those who want to try this, I have to move this into Linux. If you want to compile this, compile with, you do GCC, pthread, or is it lpthread? I have to remember whether it's this or some. And you need pthread. You need to. I think it's just pthread, and then the name of the file, maybe myfile.c. Right. I hope people are understanding the point. The reason why I'm adding, I think it's this. I'm adding this. That when you are compiling, sometimes there are some libraries that won't come automatically. So even though you are trying to use a function called pthread_create, he may not be able to compile the code, right? Because the compiler doesn't know that you're using a library. I know it's kind of annoying. It should have been that so long as you include it in the header, it should what? Automatically go and find it and compile. If it doesn't go and find it and it complains that it can't find the function call, the system call. Remember when we were doing, there was one that we just did right now where we had to use something like this one. We had to use GCC LRT. We had to do this so that it would compile, right? And so, for this one, did I do something different for this? Maybe not. Okay. I remember some of them. It comes into my mind. It comes and goes in interesting ways. When I'm doing it, then it comes, and when I finish it, it's gone. Okay. So when I see the code, then I remember what I was doing. Okay. So when I see this, it should remind me that I am supposed to use pthread. Else, when I compile, it will fail. Right? It will say it can't find the library. Right. Now let's do a very interesting trick. So it's 10 minutes to time. We're going to do something very cool. Hopefully. Right. Now, some people have been asking me, how do I move data from one? There are many ways. I lied. There are many ways to move data between one and another. I made you use the online server. But now you are used to the online server. Let us use what? Your own server. Yes, I lied. Or I didn't expose all the information. I think that's the appropriate word. So if you go to settings, right? A second way you can expose information. So I was thinking about the question she asked last time. How do you get data out? Port forwarding, right? So if you go to port forwarding, so I hope people are realizing what I'm doing. In your VirtualBox, right, there is the settings for your VirtualBox. Choose that one, right? And under network, you will find port forwarding, right? So you've been doing sockets now, and what a lot of people are doing is they want to be able to send information from the Windows to the Linux, and the Linux to the Windows. You want to now have this excitement in your life with all these programs on your system. So the way you do it is, in port forwarding, you can say, for example, that port 1022. So what it's saying is, if Windows says port 1022, it will send it to what? The VirtualBox on port 22. So that means he's forwarding every information that will come to this machine on port 1022. It will be sent to this VirtualBox on port 22. Right. Now, the benefit of this is, for some of you, maybe you are writing an application, but the application only works in Windows, but you want to write in Linux, and you don't have only Linux boxes. You can have a virtual machine, and then tell him that what? He should send information on one port into the virtual machine. Right. So if I have something that is only Linux, and I want to still have a Windows machine run it, and distribute to the world, all I have to do is what? Set the port, the host port, and tell it what? Send to the guest. So let's have some fun with this. I'm going to do the party thing. So last time we said we can do party to send information from one machine to another. Right. So computer. I hope I can find my party quickly. I have 7 minutes to find my party. 5 minutes to find my party. Okay, so that means people are also off the hook for today as far as the quiz. So I wanted to do it. So as I said, I'm out of time. So I'll try and just do my normal. Okay. Oh. Where is my party? Okay. I found my party. All right. My party. So there is what? There's party and party SFTP. Right? It's very short. All right. She's asking for what's going to be on the mini exam. Okay, so this is party. So nothing specified. So I can say, for example, open 1022. Sorry. Oh, why isn't he minding me? Did he close? Okay, I have to wait. No, he's not minding me. Okay, let me use another one. Why isn't he minding me? He's supposed to always mind me. Okay. Okay, so let's do this. You were supposed to put in the address. So I'm my own machine. So localhost 1022. Meaning it's going to send to 1022. But because of the port forwarding, it will what? It will hit my VirtualBox. It won't leave my machine. So let's... Okay, so it's connecting. Good, it's asking for my login. So login as root. Right. So you can see that the files that were in my machine, they are the same ones that are being listed here, right? There was things like, I was in shared disk folder. I was looking at, some process code, and we just looked at name pipe server.c. Isn't it the same thing? FIFO, all of that excitement. Right. So it means that if you have two machines, right, one can be virtual, but you can forward the information from your Windows machine into your Linux machine. So that what? When you are doing this, so a lot of your applications where someone says, I want to test and see how it's going to work, you can use this approach to test your code. Right? So you can have Windows run some of the Java and the Linux run the other part. So you can properly simulate sending information from one to the other. All right. So what's going to be on the mini exam is everything up until last Monday. Right. So chapter 1 is fair game, everything in chapter 1. Chapter 2, fair. Chapter 3, which was processes, fair. Chapter 4, threads, but not everything in threads. We hadn't done C threads, so C threads are not included. Just the little Java threads, like how do you create a thread, how do you start a thread. The little things we did in class, yes. Right. But we didn't do locks. There was nothing on locks, so we will not do locks. Locks will come up later. So for the code, everything C, including threads. So how do you start a thread? They should be able to maybe share some information. But I'm not going to force you to do any locks. There will not be any locking code on the exam. So everything up to last Monday. No, it won't be a midterm. Right. So the exams are broken into pieces. There will also be another exam which will be a lot more coding. A lot of coding involved. Not. So you've seen that I've been doing things like this shared memory, pipe, all the exams I'm doing. So even this one, even if code comes, it will be ones where I ask you, what does this do? Like I had last time. Like, what does this do? What change do you have to make? What will be the output? But there will be a more exciting code-oriented exam a little bit later in the semester when people are comfortable with the different things. There is no official midterm. So we do a series of exams to cover the material. The Linux command line, yes, it's fair game. Right. But more will come. So there will be an exam which will come, which will be more just code stuff, hardcore code stuff. The Linux commands will come in this one. That's simple stuff. But you realize that things like shared memory, people are getting used to it. Pipes, sockets, P threads, Java threads. That will be another exam that will come. It won't be the final, but there will be another exam where we'll just focus on, let's learn the technical parts, test you on it. Right. So you have about 3 or 4 exams before the final. At first, I used to do one big exam, but it will be 4 or 5. Say it again. If we don't do it this way, people tend to not do it. At least this way you can learn a few things. You test it. We are done. The final will cover something small. It won't be every single thing. So the final would also focus on the things on the last part of the semester. Some general ideas. But that doesn't mean you should forget everything. Because we can apply some things from here to solve things later. Okay, so thank you very, very much.